hey, there are two different theories, two different experimental predictions, and here's an experiment that one needs to do to test which one of these has nature selected. And so that was the experiment that I went to UC Berkeley and actually performed.
Your experiments are based around the concept of entanglement. Maybe if you can go back for the beginning of the quantum mechanics, how it was started and the basis of it. So there was two major things in quantum mechanics, let's say superposition, which is comprehensible, but then another thing is entanglement, which was introduced, and then I think that started to bring the famous paradox.
Okay, so
talk about
there
that.
were actually two formulations of quantum mechanics done by Schrödinger. Schrödinger produced actually two very different equations. The first one predicted the spectrum energy levels of hydrogen. It was an instant, overwhelming success. Everything you could calculate, all of the details of the structure of hydrogen were precisely calculated using Schrödinger's first equation. He subsequently produced a second equation, moving up the periodic table to helium. Okay, now hydrogen has one electron. So the first equation describes one particle systems. Helium has two electrons. A very different equation is needed to handle two particle systems, e.g. helium.
It's like a system of equations in this case? Or
Well, it's a single differential equation. The basic difference is that the first equation is formulated like a wave equation, just like in real space-time, just like electromagnetism, Maxwell's equations, sound waves. There are real waves, ocean waves propagating in three-dimensional space and time, objectively real entities. You can see them. The Schrödinger's second equation for helium, totally different, and nobody seemed to pay much attention to this dramatic difference. It was formulated in what's called configuration space. The argument of the wave function is not the position in space where the wave function is defined. It is the value that depends on the positions of the hypothetical positions of the two electrons, not the position where you evaluate it. It just depends on the system being studied. The Schrödinger's first equation is true. The physical space does not depend upon the system being studied, whereas configuration space of Schrödinger's second equation is strongly dependent on the number of arguments of the wave function. It depends on the system being studied. The structure of space should not depend upon the number of particles that you are considering. Space should exist whether or not, no matter what you put in it. Nonetheless, so Schrödinger's second equation, yes?
Maybe stupid question, but hydrogen actually has two particles. It has the proton and the electron.
Yes, that is a tricky bit. The tricky bit that is the way that people account for that is that they reduce the hydrogen atom, the solution of Schrödinger's equation, to a single particle system by calculating the position of the electron in the center of mass system. So we really now have just a way one would do this in classical mechanics. One works in the center of mass system. So there's really now only one variable, which is the position of the
electron
relative to the center of mass. And so one, using that cute trick, reduces the Schrödinger's first equation, which really sneakily has two particles, as you point out, down to a single particle system. You can't do that. It doesn't work. So there you have no choice but to move to a configuration space formulation. What the surprise that came out of this, and both Schrödinger and Einstein were very disturbed by the result, is that Schrödinger's second equation had unanticipated solutions. Schrödinger's first equation was straightforward. It predicted probability waves propagating in space. Schrödinger's second equation did not do that, but it introduced the whole new phenomenon of entanglement. That the two electrons, that their solution, rather than being just a simple sum of eigenstates, was a sum of products of the various eigenstates of the two individual particles. What does this mean? These entangled state solutions show that there is a very strong correlation between the motion of the two electrons. Now, people at the time thought, oh, well, okay, of course, the two electrons are intimate in a helium atom, are intimately connected with each other. They're continuously talking to each other, if you will. So it'd be hardly surprising if their motions were not highly correlated. But what Einstein and Schrödinger independently noticed was that this intimate correlation in their behaviors was independent of their separation. That you could take the two electrons, put them as far apart as you wanted, and they would maintain this intimate correlation. This was quite surprising and shocking, and was very disturbing to both Einstein and Schrödinger. And so what Einstein did was he thought about this a lot and realized that this produced what became known as the Einstein-Podolsky-Rosen paradox. That he assumed that the two particles, if you move them far enough apart, there was no way they could communicate with each other. But what the Einstein-Podolsky-Rosen paradox showed was a very famous paper in 1935 that he published, and Schrödinger also published a companion paper. What Einstein showed was this intercorrelation existed, and that effectively this violated what he thought was a prediction of special relativity, prohibiting you from sending signals faster than the speed of light. So Schrödinger's contribution at that point was also very interesting. He proposed, and Wendell Fury at Harvard also proposed in parallel, another idea, which was that, well, maybe something wrong with quantum mechanics, that perhaps this entanglement disappears when the two electrons are no longer intimately in the vicinity of a helium nucleus. When you move them very far apart, maybe this entanglement somehow disappears. They both Fury and Schrödinger realized, whoops, if that's true, then the predictions of the quantum mechanics must be wrong, so therefore, obviously, that theory is wrong. Everybody at that point believe that the predictions of quantum mechanics are perfectly correct. End of story, no longer an interesting problem. So then along comes John Bell in 1964. He was trying to understand this correlation, and the title of his paper was on the Einstein-Podolsky-Rosen paradox. He viewed it as a paradox. And he made this absolutely startling discovery. He showed that if you tried to formulate the two-particle system of two separated particles, two separated entangled state particles, in a physical space that one could not get the predictions of quantum mechanics. Now, his idea at the time, he again was assuming that predictions of quantum mechanics are obviously true, and so he didn't even consider doing an experiment. In fact, the whole world, except for my associates and me, were the only people around who thought, well, gee, maybe we ought to experimentally test all of this. So we generalized, Simone, Mike Horn, and I, and Dick Holt and I generalized his work to show, hey, there are two different theories, two different experimental predictions, and here's an experiment that one needs to do to test which one of these has nature selected. And so that was the experiment that I went to UC Berkeley and actually performed.